So I'll redraw the 26,900 pound vector down here. Now, I can think of this vector as being composed of both a perpendicular component and, as its hypotenuse, member DF. Okay, so this is member DF down here, this hypotenuse. I know the length of this side is 26,900 pounds. And I need to find this angle for DF. Well, if I think about, if I change ink colors here maybe to make this a little clearer. If I think about this entire angle is 90, and I'm interested in this remaining portion here between this new vector I've drawn and member DF. Well, probably the first step to that is figuring out what angle DF is relative to like a horizontal and a vertical line. So let's start just thinking about kind of what we know about this triangle here. I can draw in a perfectly horizontal line here, perfectly vertical line here. This horizontal line has a length of 10 feet. This vertical line, well, it started at 12 feet in height, it ended at 14 feet in height. This has a length of 2. Let's think about what else we know here. This angle is in a triangle that's got a length one side 10 feet and the other side 12 feet. So if I think about this as like angle A, and I think about this as angle B, this included angle here, actually this included angle we can calculate. I'm going to call this angle A. I'm going to call this angle question mark. That's the angle we're trying to find. Well, what do I know? I know that A plus B plus the angle we're trying to find must add to 90 degrees. So now I go to work. Okay, angle A. Well, angle A is the included angle of a triangle with an adjacent side of 10 and an opposite side of 2. So turns out that I can just use the inverse tangent function to find that. So if I say tan to the negative 1, 2 divided by 10 is 0.2. And this actually works out to 11.3 degrees. Then I can look at angle B. Angle B has got an adjacent side of 10 and an opposite side of 12. So I can take the arctangent or the inverse tangent of 12 divided by 10, which is 1.2. And that one I've got to punch up. So I'll come over here to my calculator. 1.2, I hit the inverse key to get the inverse tangent function, and I find that it's about 50.2 degrees. So if I take my 90 and I subtract from it, so I'm going to make this a negative number and I'm going to add it to 90. So that's like 90 subtract 50.2. And then I subtract from that another 11.3. I find that this included angle A is about 28.5 degrees. So this angle in here is about 28.5 degrees. Well, if this is 28.5 degrees, I have the adjacent side, and I'm trying to find the hypotenuse. Now I can just use the cosine function. So cosine 28.5 equals adjacent over hypotenuse, so 26,900 over the hypotenuse. I multiply both sides by h, they cancel on the right, and I divide both sides by cosine 28.5, they cancel on the left, and I get that the hypotenuse is equal to 26,900 pounds over the cosine of 28.5. So if I punch this up in my calculator, I can just take the cosine of that angle, and I'm going to add that, I'm going to put that in the memory. And then I'm going to take 26,900 and divide it by the number that's in the memory. And I get about 30,600 pounds, give or take. Now, if I look at point DF, imagine I cut DF. What would happen? Well, this whole thing would kind of fold up about point G, right? Point D would move to the right, point F would move to the left, and that tells me that this is in compression. So the last thing to figure out are the forces in DG. And let's think about what I know. I could figure out, if I know that the force in DF is 30,600 pounds, I could figure out the leftward thrust here, and I could figure out the rightward thrust here. I know the rightward thrust here, and from that I could get the horizontal component of DG. So for the last part of this problem, I want to use method of sections. I think that's going to be the easiest way to sort this out. So I'm going to section this truss right along this line. And I'm going to redraw kind of these three components down here. So I have component DF. I have what's kind of left of component DF. It's pushing down and to the left. I've got component DG, which is in this position. I don't know yet what the force is. And I got component EG, which is in tension, is pulling kind of the sectioned part to the right. So for each of these, I want to think about, in this case, I'm going to use horizontal force to solve the problem. I want to think about what is the horizontal component of this force of DF, and what is the horizontal component of the force of DG, or EG, excuse me. So EG, I already know, is going to be 23,300 pounds to the right, because it's in tension. It's pulling the section towards point G. For part DF, well, I know that the total force in part DF is 30,600 pounds. And I know this included angle in here is about 11.3 degrees. And this would be the adjacent side, so I can use the cosine function. So cosine of 11.3 degrees equals what? Well, it equals adjacent over hypotenuse, which is 30,600. So now we'll just multiply both sides by 30,600. On the right, these cancel, and so I get 30,000 times 600 is 30,600 times the cosine of 11.3 is going to be the horizontal force. So I'll clear out of here. So I start with the angle, 11.3 degrees. I take the cosine of it, multiply that by 30,600, and you can see that I get about 30,000 pounds of horizontal force. So component A here, this horizontal thrust is about 30,000 pounds to the left. So now I start thinking about, okay, I've got a 30,000 pound force pushing this this section line here that we've drawn up here in the diagram to the left. I've got a 23,300 pound force pulling it to the right. Well, that means that the horizontal contribution of DG has got to be the difference of those two, which is 6,700 pounds, right? So if I think about the 30,000 as being kind of like a negative number because it's to the left, so I take 23,300 and I subtract from it 30,000. I get a 6,700 pound force. So as I think about member DG, let's redraw this triangle. All right, so here's point G, here's point D, here's point E. What do I know? I know this triangle is 10 feet on this side, it's 12 feet on this side. If I want to think about it in terms of force, it's 6,700 pounds on this side. And the question becomes, what's the force up here in the hypotenuse, which we don't know. Another thing I can think about is this in tension or compression? Well, if there's a 30,000 pound thrust leftward at the top and a 23,000 pound rightward thrust on the bottom, this has got to be in tension. So the question is, how do I find the actual tension using the hypotenuse? Well, I can think about what is this included angle. Well, this included angle is the angle that's created when one side of the triangle is 10 and the other is 12, which we've already figured out was 50.2 degrees. So I'm trying to relate the adjacent side to the hypotenuse. I know the angle, so now it's just a matter of plugging and chugging. Cosine of 50.2 equals adjacent over hypotenuse, 6,700 over the hypotenuse. I multiply both sides by h. On the right side they cancel. I divide both sides by the cosine of 50.2. And that's going to give me my value. So again, when we're using the calculator, we have to start with the angle 50.2, and I take the cosine of it, and I'm going to add that to the memory. And then I'm going to take 6,700 and divide it by what's in the memory, which is the cosine. And there you see that we get right around 10,400 pounds. Actually, we could probably call it 10,450 pounds, give or take. And again, that is tension due to the fact that this, if you think about DG, it is pulling point D to the right. So that was quite a bit of work, but you can see that through the process of method of joints and method of sections, we were able to figure out all of the forces in these members. And of course, we could keep going. We could find every force in every member in this entire structure, and that would give us some evidence as to how we would expect this to collapse under fire conditions.